So the year is 1886, and a guy by the name of Heinrich Hertz is carrying out experiments in Germany. So this happens to be about 11 years before SUU was founded, so it doesn't feel like that long ago, even though SU was founded more than 100 years ago. He was using an antenna, is what we would call it today, but really what it was two pieces of copper wire that extended out from a point, and they didn't touch in the middle. And he'd apply a very high voltage in between the two pieces of wire, and he'd get a spark, basically, that would arc between the two of these. We actually have a version of this very apparatus, which is who knows how old, in the physics lab, and I wanted to show it to you. Okay, so this is the experiment that we wanted to show you. This is the one from Heinrich Hertz. So if you look over here, you can see that there. You have the transformer on the table. And right next to it is this weird thing that looks like a bizarre antenna here. So let me go ahead and get this turned around. You have two panels here. One panel on this side, one panel on this side. And you can see they're separated by a short distance here. What Heinrich Hertz was doing was he was taking a transformer and putting a spark between the two of these antennas. So the thing that Heinrich Hertz was seeing was that when there was a spark across the first gap on the first antenna he was applying the voltage to, another spark would appear on another set of antennas somewhere else in the laboratory. And he was deducing that it was electromagnetic disturbances or waves from the first set of antennas that was the reason for this second sparking. We can't actually create that second spark, but what I have right here, if you can see, I have a second set of antennas, and I've attached those to an amp meter. You can see right now it's reading 0, because it is reading 0, right? Okay. So what I'm going to do is I'm going to plug in this transformer, and we're going to get a bit of a spark. You can see that there it is. There's the spark that's forming. And right now what's happening is the electrons and charge are just sloshing back and forth across these antennas, and like objects moving through water, it's sloshing, creating electromagnetic waves, which are being picked up by this antenna and sloshing around the charge in it. So now if we look at the amp meter here, you can see that there's a little bit of current that's flowing through, sort of as a result of the fact that these electromagnetic waves coming off the first antenna are in fact inducing some type of a current through the second set of antennas. So what this experiment shows, in a nutshell, is that electromagnetic waves are a thing. Basically what's happening is, as a spark arcs over the first two antennas, charge is sloshing back and forth across those antennas. And just like if you can picture two sets of balls in water, if I were to grab these balls and drag them through the water, accelerate them through water, you create water waves, essentially. And so this is the phenomena that Heinrich Hertz was seeing. So electromagnetic waves are a thing. Around the same time, there was a guy by the name of James Clerk Maxwell, who took all of Faraday's work and formalized them in a set of 4 differential equations, which we call Maxwell's equations, and they're the governing laws for all of electromagnetism. What Maxwell's equations predict, if a changing magnetic field produces an electric field and a changing electric field produces a magnetic field, if you have a wave of electric influence, that's a changing electric field, and it generates a magnetic field, which itself is changing and also generating an electric field as well. And so it shows that electromagnetic waves are essentially possible. And this is what Heinrich Hertz was observing in his laboratory, were these electromagnetic waves. There's one more experiment that we wanted to show you real quick to kind of demonstrate in some way that light is a wave, that it really has these wave-like characteristics. Young and company carried out an experiment where they had a card, and inside the card there were 2 slits. And they shone a light on the 2 slits. And they want to know the pattern that would appear behind the 2 slits. Well, that's all good and well. You'd think that would be a really boring experiment to carry out. You'd expect to see a silhouette, basically the shape of the card with 2 bright spots representing the 2 holes of the 2 slits in the card where the light's leaking through. But if you put those holes extremely close together, it turns out that a different phenomenon appears, and this is called the interference pattern. Literally what this is it's my laser, and I have it pointed at a card here. And on the card there's a set of 2 slits, and the laser is going to shine through those 2 slits. You can see that I'm going to try to sort of reproduce this experiment in the lab. It's really hard to see on this camera here. But you can see on a note, there's a series of spots actually running vertically along the wall. There's a bright patch in the middle, but running upwards vertically from that, there's bright spots followed by interspaced by little dark patches. And this is the famous interference pattern. So as you can tell, that's not a silhouette of like the individual holes in that card. This is a different pattern that's arising as the light from coming out of those two holes interferes with itself in a kind of a complicated wave-like way. And so to kind of show you that in a way that sort of makes more conceptual sense, you can take an analogy with water. Water waves aren't exactly like light waves, and we'll talk about why tomorrow. But you can still kind of do this and get sort of an idea of why it works. You can see there's this pool of water that I have here. And there's a little machine, there's two balls that are sitting inside of that pool of water. And as they vibrate, they're going to create waves, much like the two slits in the card create waves as light passes through them. And what we're going to look at is how these waves interfere with each other when the sources of those waves are so close together. This is kind of hard to see. Let me get an angle there. Can you see how there's regions where there's high amplitude waves and there's regions where the waves cancel out? They radiate outwards from between those two spikes. And the way we explain it is with this type of water that we were talking about before. There's bright regions and then there's dark regions on the screen. And the bright regions are where the waves from the two holes, as they emanate outwards as spherical waves, wavefronts, the regions where these two wavefronts constructively interfere and create bright spots, and there's regions where they destructively interfere and cancel out and create these dark fringes. And so this pattern of light and dark fringes is what Jung observed, and they considered this evidence that light was, in fact, electromagnetic. So, what we're doing right now is we're setting up one of the greatest advances in physics. Light is a wave, and that's going to play into... Light is a wave, and that's going to have a profound influence on a thinker that you know really well from popular culture, and that's Albert Einstein. Albert Einstein is going to redefine the way that we think about space and time. And it starts with this bizarre substance called light, and its enigmatic properties as being a wave. So anyway, stay tuned for that. Try out the homework. It's not going to be as hard as you think. Get down through the first section. There's a series of formulas that I didn't introduce in this video, but they're really easy to use if you know how to plug in numbers. So just pound your way through that and you'll be good. We're thinking about you guys. Take care, okay? Bye.